All right, let's get into it. We're going to unpack the story of how Apache Spark's stream processing came to be. And it's a story that honestly totally changed the game for how we deal with real-time data, moving from these complex, fragile systems to something that's surprisingly elegant and incredibly tough.
So this is it, right? This is the million-dollar question in big data. It's not just about being fast, it's about being perfect. When a server inevitably goes down right in the middle of processing, how do you make sure you can pick up exactly where you left off and you can't lose a single event or count it twice? Spark has come up with a truly brilliant answer to this.
So here's how we're going to break it down. We'll start with the huge problem Spark was designed to fix, then we'll look at its first game-changing idea, see how that grew into the modern approach we use today, and finally we'll peek under the hood to see the magic that makes it all so reliable.
So before Spark really came onto the scene, stream processing at a massive scale was, well, it was a real headache. The bigger your system got, the more you just had to accept that things were going to fail or slow down. And the old ways of doing things had some major problems with both cost and reliability.
And you can see here, the old way of doing things forced you into some really tough spots. The main approach used these continuous operators, basically tasks that ran forever and had to remember a bunch of stuff. To make them not break, you either had to replicate everything, which literally meant paying for double the hardware, or you had a backup system that took forever to recover. And why so long? Because if one machine failed, a new one had to painstakingly rebuild everything that was lost, step by step. And on top of all that, you had this straggler problem, where just one slow machine could bring the entire system to its knees.
And this is where Spark's first big revolutionary idea comes in. They just decided to completely flip the script. They said, let's stop thinking about a stream as this one endless, continuous thing and think about it in a totally new way.
And you can really see that shift right here. Instead of one long-running, messy process that's hard to manage, Spark's D-Stream model said, hey, what if streaming is just a whole bunch of really small, really fast, predictable batch jobs? This is that famous micro-batch architecture you always hear about.
The process itself is actually pretty simple, but it's incredibly powerful. You just chop up the live stream into tiny little windows of time. The data in each little window becomes its own tiny, unchangeable dataset. And then Spark just runs a quick, predictable batch job on that little dataset. It's this micro-batch idea that's the foundation for all of Spark Streaming's resilience. Okay, and the absolute key to making this work is something called lineage. Just think of it as a recipe. Spark remembers the exact recipe, every single step, it used to create every piece of data. So if a machine fails and some data disappears, Spark doesn't panic. It doesn't need a backup copy. It just pulls out the recipe, the lineage, and recooks that missing piece of data. And it can do it across tons of machines at once, which makes recovery super fast, and you don't have to pay for twice the hardware. Okay, so that was the first big leap. But now let's fast forward to the modern era, because things got even simpler and way more powerful. The team behind Spark realized they could hide even more of the complexity.
And this quote from Databricks, it really says it all. The whole philosophy behind structured streaming is that you, the developer, shouldn't have to worry about the nitty-gritty details of streaming. Building a real-time app should be as easy as working with a normal database.
All right, this next idea is maybe the most important concept in this whole thing. Just picture it. A data stream isn't some weird, complicated thing. It's just a table that never ever stops growing. Every new piece of data that comes in is just a new row getting added to the bottom of this infinite table. That's the whole idea. So with this model, your job as a developer becomes so much easier. You just write a query on that infinite table, exactly like you would with any normal SQL table or a data frame. Your query stays the same, and Spark does all the heavy lifting in the background to figure out how to keep the results updated as new rows come flying in.
And here's the proof, right? This is where the magic really happens. Look at this code. This simple word count could be running on a file that's just sitting there, or it could be running on a live, real-time stream from something like Kafka. The code is exactly the same. You write code that looks like a simple batch job, and Spark just automatically makes it work for a live stream. It's just an incredible simplification.
Okay, so this all sounds great, but you're probably wondering, how does it not just fall apart? How does it remember its progress or keep track of things like running counts if the power goes out? Well, the magic behind all that reliability is called checkpointing. The secret sauce here is something called checkpointing. And really, you can just think of it as a super reliable, permanent bookmark for your stream.
After every little micro batch, Spark carefully writes down exactly what data it just finished processing and any state it needs to remember. So if the job dies, it just opens up to the last bookmark and picks up right where it was. No fuss, no lost data.
And it's really important to get this next part. For a simple job that doesn't need to remember anything from one batch to the next, a stateless job, the checkpoint just has to remember its location, kind of like a page number in a book. But for a stateful job, say one that needs to find and drop duplicate events, the checkpoint is even more crucial. It has to save both the location and all the event IDs it's seen recently.
And you know, if you actually peek inside one of these checkpoint folders, it's not some kind of mysterious black box. It's actually super organized. You've got files for offsets, which tell Spark what to read next, files for commits, which confirm what's already done. And for those stateful jobs, you'll see a state directory that physically stores all the stuff it needs to remember, often as a tiny little delta table.
Okay, now this is a really common point of confusion for folks using Spark. What's the difference between caching and checkpointing? Caching, or persisting, is all about speed. It holds data in memory but keeps that recipe, that lineage, just in case it needs to be recalculated. RDD checkpointing, on the other hand, is for pure resilience, especially in super long, complex jobs. It physically saves the data to a reliable place and, crucially, it breaks the lineage. That checkpointed data becomes a brand new starting point, which is vital for preventing errors and making recovery much faster.
But wait a second, what about a job that has to remember state and run forever? If you're counting unique users, for example, does the list of users just grow and grow until the whole thing crashes from running out of memory? Nope. And that's where watermarking comes in. It's Spark's super elegant solution. You basically just tell Spark, look, I don't really expect data to show up more than, say, 10 minutes late. Spark then uses that as a moving window to safely throw away old state that it knows it won't need anymore.
And the cool thing is, all this amazing tech boils down to some really simple things you can watch to make sure your job is healthy. If you just look at the metric called max offsets behind latest, you get an instant health check. If that number keeps going up and up, you know right away that data is coming in faster than you can process it, and it's time to add more resources. It's that simple.
And that really brings us to the big, mind-bending question at the end of all of this. If we can now query a live, real-time stream of data just as easily as we query a static table in a database, what does that mean for databases themselves? Spark is blurring that line between data in motion and data at rest, and it really forces us to imagine a future where we can analyze information the very instant it's created.